The authors propose a new class of online learning algorithms, Generalized Implicit Follow-The-Regularized-Leader, FTRL, which expands the scope of the FTRL framework. This framework allows for the design of new update rules, recovering known algorithms such as Mirror-Prox and implicit FTRL, and enables the construction of updates that directly improve the worst-case upper bound on the regret. The key idea is to substitute the linearization of the losses with a Fenchel-Young inequality. The authors provide a summary of implicit and linearized updates for FTRL and OMD in Table 1, highlighting the differences between various algorithms. They also discuss related work, including implicit mirror descent and FTRL updates, and position their framework as a novel contribution to the field. The proposed algorithm is based on the FTRL equality, with a new fundamental strategy that utilizes the Fenchel-Young inequality to obtain a better inequality than the standard one for subgradients. The analysis shows that the optimal setting of ZT is the one that minimizes the function HT, Z, or HT, Z, which are defined in terms of the Fenchel conjugate of the regularizer and the Fenchel conjugate of the loss function. Under the assumptions of Theorem 3.1, the updates in equations 4 and 5 can be rewritten using the proximal operator of the loss functions, enabling the interpretation of these updates as moving by a quantity dependent on the gradient at the updated point. This implicit nature of the updates justifies the terminology, implicit updates, used in online learning literature. Moreover, the updates become equivalent to the implicit online mirror descent update for constant step sizes. The generalized implicit FTRL updates are shown to possess an advantage in scenarios with slow temporal variability of the loss functions, as quantified by a regret bound dependent on the temporal variation. This is possible without requiring the Bregman divergence to be bounded on the feasible set V, thanks to the use of FTRL instead of OMD. An adaptive regret guarantee is also obtained, and the choice of ZT that minimizes the regret upper bound involves solving an optimization problem. A viable solution is to approximately solve for the optimal ZT by setting ZT as a subgradient after one fake update, similar to the Mirror-Prox algorithm. Generalized implicit FTRL algorithms have been shown to be effective in various machine learning tasks, allowing for more flexibility in the choice of ZT. Theoretical properties of generalized implicit FTRL are established, proving that the updates satisfy HT, ZT, is less than or equal to HT, GT, and HT, ZT, is less than or equal to HT, GT, guaranteeing that the updates are at least as good as the subgradient GT in minimizing the worst-case regret. Closed-form updates for generalized implicit FTRL with regularizer psi t, x, equals lambda t, 2 parallel x squared are provided, and an empirical evaluation of different choices of ZT in algorithm 1 is conducted. The results show that generalized implicit FTRL with two-step updates performs remarkably well and could be a viable alternative to aProx updates. Here is a combined summary of pages 912 of the research paper. The authors propose a novel framework, Generalized Implicit Follow-The-Regularized-Leader, GIFTRL, which provides a unifying framework for designing new algorithms with low computational complexity. This framework can recover known algorithms, such as implicit FTRL and FTRL with linearized losses, and offers a theoretical guideline for designing new algorithms. Experimental results, as shown in figures 2 and 3, demonstrate the robustness of implicit FTRL updates and the sensitivity of FTRL with linearized updates to the choice of hyperparameter beta. The authors acknowledge the contributions of Alex Stoff and funding from the National Science Foundation. The paper concludes by highlighting the main contribution of providing a general, flexible, and theoretically grounded framework for designing new algorithms with low computational complexity. The authors then build upon the concept of GIFTRL, citing various works on optimization, online learning, and proximal algorithms. They provide proximal operator formulas for common losses, including the hinge loss, absolute loss, and squared loss, which are well known and can be found in existing literature. The authors proceed to prove corollary 4.3, which provides an upper bound on the regret guarantee, using the proximal operator formulas and the Fenchel-Young inequality. They derive two different upper bounds on the term n-ary summation t equals 1 t gamma t, involving the difference in losses between consecutive rounds and the Fenchel-Young inequality, respectively. The final upper bound on the regret guarantee is derived using lemma 6.1 from Campolongo and Orabona, 2020, involving the sum of the norms of the gradients and the learning rate. The authors also provide the proof of corollary 6.2, which involves the proximal operator of the surrogate loss function Lt lambda. Throughout the proofs, the authors utilize various mathematical concepts, including convex analysis, monotone operators, and proximal algorithms, to establish the desired bounds and results. The Generalized Implicit Follow-The-Regularized-Leader (GIFTRL) algorithm is introduced as a novel approach for optimizing machine learning model parameters. This algorithm iteratively updates model parameters using the gradient of the loss function with respect to the model's parameters, repeating the process until convergence or a specified number of iterations. The GIFTRL algorithm's main contribution lies in its ability to adaptively adjust the learning rate based on the model's performance, ensuring efficient and effective optimization. The algorithm's adaptive learning rate adjustment is facilitated by the use of a proximal operator, which is defined as the proximal mapping of the scaled loss function. This proximal operator is used to compute the gradient of the loss function, allowing the algorithm to adapt to the model's performance. The GIFTRL algorithm's update rule is given by equation 3, which combines the gradient descent update with the proximal operator. Theoretical analysis of the GIFTRL algorithm reveals its convergence properties, with a proof of convergence provided in Theorem 1. The theorem establishes that the algorithm converges to a stationary point of the loss function under certain conditions on the step size and the proximal operator. Empirical evaluation of the GIFTRL algorithm on several benchmark datasets demonstrates its competitive performance compared to state-of-the-art optimization algorithms. The results, presented in Table 1, show that the GIFTRL algorithm achieves improved convergence rates and smaller final losses compared to other algorithms. The algorithm's adaptability to different learning rates is illustrated in Figure 1, which highlights its robustness to varying learning rates.